you know roughly what a magnet looks like, you can actually get a glimpse of these if you go down the first floor of Build Your Audition. And so the magnet stands on legs. This is the magnet. And it's a double viewer flask. It's a double thermos. And so you have a layer on the inside which is filled with liquid helium. And then on the outside you have liquid nitrogen. And the reason you need to keep it that cold is because these are superconducting electromagnets. And the helium slowly boils off. Nitrogen, not a problem, it's cheap. Helium is expensive. When you go home, take a look and see where helium comes from. It turns out that we're going to run out at some point. And so it's not clear exactly how you run NMRs or MRI imaging machines, which run on the same principle without liquid helium. The reason we need to go that cold is because we so far have no superconducting materials that work at higher temperatures than liquid helium. So the sample goes right in the middle. There's a hole in the middle. The sample goes in there, and the sample is spun around its vertical axis at a high speed to average out any inconsistencies in the signal. And the coils, the RF coils, surround the sample. And so it's kind of an interesting engineering feat how they made this thing work. But as I said, if you're interested, you can go down and take a look at it in the first floor of Vision. Okay, so let's pick up where we left off last time. Last time we talked about the difference in chemical shift between the CH2 and the CH3s in dimethoxymethane. And we said that the CH2s came at this chemical shift, and the CH3s came at this one, and now we need to figure out what that's trying to tell us. And so by plugging in numbers into the fundamental equation for NMR, we find out that the frequency for the CH2s is greater than the frequency for the CH3s. That's what it means when you have a spectrum that looks like this. This frequency is bigger than that one. The frequency, remember, is measured from the standard, which is tetramethylsilane. So we're actually looking at this difference in frequencies here. Okay, so we look at these frequencies, and one is greater than the other. And then because we know frequency is proportional to field, then it means that the two fields have the same relationship. This is a constant, that's a constant. That means that the magnetic field that's experienced by the CH2 is actually greater than the magnetic field that's experienced by the CH3. So this is going to be true for any peaks on the spectrum. So peaks that appear here experience a larger field than the ones, I'm sorry, smaller field than the ones that appear here. So as I go from right to left, the field increases. And so now the reason for that is why. I mean, the applied magnetic field, the electromagnet, applies the same field to everybody, right? It can't discriminate. But at that proton, the field here is greater than the field there. So the effective magnetic field at CH2 is larger. So what that means, what we say is that the CH2 is de-shielded relative to the CH3. All that means is that it experiences a higher effective magnetic field. So I've talked about this. This is I mentioned that last time, so I don't need to go over that again. So remember that the effect of that causes that shift has to do with the electronegativity of the oxygen atom. So in other words, if I have carbons or protons that are close to electronegative atoms, then those are going to be de-shielded. So if that's the case, then we should be able to say something about the relative electronegativity of the atoms. Here it was oxygen atoms, but it didn't have to be. It could be chlorines or fluorines or nitrogens or whatever. And anything more electronegative than carbon. And we should be able to say something about the chemical shift. So the reason NMR is such a useful tool is precisely because we can make strong correlation between the chemical shift and the chemical environment. Namely, the chemical shift and whether we have an oxygen or a nitrogen or another carbon or whatever bonded to the carbon where the hydrogens are. So let's take a look at the simplest case. Okay, so the simplest case is methyl. And so I'm going to have methyl fluoride, chloride, bromide, iodide. Okay, so I'm just going to look at the halogens. Now, you all know that fluoride, or fluorine, pardon me, is more electronegative than iodine. So what I've listed here is an electronegativity scale. There are a bunch of electronegativity scales, you know, that measure electronegativity of atoms. Pauling, I think this is Linus Pauling's scale, if I'm not mistaken. He, I think, has one of the ones that's most commonly used. It's not the only one. The various scales differ in the absolute numbers, but the trends are always the same. So what we can say is fluoride more electronegative than chloride and so on. And so electronegativity is increased in that direction. You'll notice the chemical shifts also increase in that direction. And so as the halogen becomes more and more electron withdrawing, the signal for that methyl moves further and further to the left in your spectrum. And so you can predict whether you have a chlorine or bromine or whatever just based on chemical shift. The other thing I want you to notice is that the effects are additive. So if I have one chlorine, it comes at the methyl shows up at 3.05. If I have two chlorines, 5.3. Okay, so that's because I have two chlorines and not one, pulling electron density out of that carbon. Because they're pulling electron density out of that carbon, those electrons are not able to shield the CH2. Remember, the shielding effect is caused by circulation of valence electrons that induce a magnetic field that typically opposes the field that's from the magnet. So if those electrons are not there, then they cannot shield. So pulling away electrons means de-shielding. Once you get up to chloroform with 3 chlorines, you're all the way up to 7. Okay, so that methine, that CH, comes all the way up there. Okay, so the effects of each electronegative atom adds onto the effect. Now, the origin of this effect is what we discussed. Electrons induce a magnetic field that typically opposes the applied field from the magnet. Okay, now another trend, so that's one trend, very general trend that we can exploit for determining structure. Here's another one. Methyls are always going to be shielded relative to CH2s, relative to CHs. Other things being equal, okay, always. So other things being equal, methyl group is going to be off to the right, methylene will be displaced to the left, and the methine displaced from the methylene to the left. So that's so this is more shielded, less shielded, okay? Now, take a look at what happens here. So here I have a methine, it's got 2 alkyls and a chlorine, that comes around 4. If I take away the chlorine and I put a CH3, but now I have a vinyl group, it's at 2.63, so big difference here. And then if I have a chlorine and a vinyl group, then it moves even further downfield from here. So this is more de-shielded than that. So what that tells you is that the sp2 hybridized carbon is de-shielding that proton. Now, why should that be? Why should a sp2 versus sp3? Why should the sp2 hybridized carbon, sp3, sp2, why should the sp2 one induce the proton here to occur at the signal to show up at a higher field? Why is it electron withdrawing? Well, because it has more s character, right? The s orbitals are close to the nucleus, yada, yada, yada. You've heard this all before. So it's completely consistent with what we said about what? About pKa of alkyne versus alkene versus alkane. That was the last time we talked about that. And so the presence of a sp2 hybridized carbon atom pulls electron density out of this bond, polarizing it towards the sp2, meaning that this is now heat shielded. Okay. So now we need to do something that's kind of hard. We need to remember some stereochemistry. Stereochemistry is always a challenge. So remember that way back when, probably you can't remember, which means we need to review, we talked about chemical equivalents and stereochemical equivalents. And now it comes back. I told you at the time that this was going to come up again when we talk about NMR. Well, here it is. So, so we're going to be interested in the same molecule. If we have, a proton here and a proton there, are those going to give separate peaks in the NMR, or for some reason are they going to be under the same peak? And the rule is this, that if they are stereochemically non-equivalent, then there will be chemical shift non-equivalent too, which means stereochemical non-equivalence means you're going to have two different peaks, okay, for two protons. So what does that mean? Well, if you have homotopic protons, those are always going to be under the same peak. So homotopic are always chemically equivalent, they are stereochemically equivalent, and they are chemical shift equivalent. So homotopic you don't have to worry about. What does that really mean in real life? Well, in real life it means this, that if I have methyl chloride, okay, these protons are all homotopic, and so they appear under the same peak. There's one singlet for methyl chloride. Why? Well, because these are homotopic, they're stereochemically equivalent, therefore they are chemical shift equivalent. Okay? They are equivalent, so yeah. So this is true and the opposite is true. It's equivalent to equivalent. So homotopic protons always going to have the same chemical shift. No argument there. Diastereotopic protons, on the other hand, probably have different chemical shifts. Now, why am I hedging? I told you last time. I'm hedging because, yes, they have different chemical shifts, but that difference may be tiny. And if it's small enough, and your spectrometer is, say, 300 megahertz and not a 600, then that little tiny difference in chemical shift may be too small for you to see. And so, if they are diastereotopic, they probably have different chemical shifts. Okay. Now, enantiotopic protons, that's just what I said. Enantiotopic protons, those are almost always going to have the same chemical shift unless, and I can't think of a problem or an experiment that we're going to discuss, but it's nevertheless the case, unless the experiment is done in the presence of a chiral non-racemic solvent or some chiral non-racemic molecule that associates with it. So in other words, if they are enantiotopic protons, typically you're not going to be able to distinguish them by NMR unless you have some asymmetric solvent in there that makes them diastereotopic. Okay? So this is a little bit hard to understand right now, but you don't need to worry too much about that. Think about it later. It should make itself clear. So the enantiotopic protons have the same chemical shift in an achiral environment. Now most of the achiral environment is the NMR solvent. The solvents that we typically use, for reasons that you're going to find out, are deuterochloroform. This stuff here are deuterobenzene. So notice no protons. The protons here have been substituted by deuterium, and you can figure out why that is. Let's take a look and see kind of an example here. Okay, so here I have 2-chlorobutane. And so the question is, how many signals do we expect to see in the proton NMR? Well, we need to figure out, first of all, how many chemically or stereochemically non-equivalent protons do we have. The other thing that I don't mention, but you guys already know, that if the protons are on different coordinates, so for example this one and this one, or have different connectivities, then obviously those are going to be stereochemically non-equivalent. So if they're constitutionally non-equivalent, then they're stereochemically non-equivalent. So a priori, we have how many constitutionally non-equivalent groups of protons? Constitutionally non-equivalent protons. How many groups? Quickly. constitutionally? 4. 1, 2, 3, 4. Okay, are these going to be stereochemically equivalent?
Yes. Yes.
No. These are distereotopic because this is a chiral center. So you expect to see 1, 2, 3, 4, 5 peaks for that. Okay, go back and review chapter 10. Okay, you need to do that. These two are distereotopic. Why? Well, because if I color one red and then color the other one red, those two compounds are going to be diastereomers. So these two protons are diastereotopic, and therefore they are stereochemically non-equivalent, and because they're stereochemically non-equivalent, they are chemical shift non-equivalent. And so here, yes, 1, 2, 3, 4, 5 peaks. I know it's easy to forget that stuff, but please do review chapter 10 because you need to remember that stuff. Okay, now there's also a problem, as I said, of accidental overlap, right? I mean, peaks that are stereochemically non-equivalent may, the non-equivalence may be tiny, you don't see it. It can happen. But what you need to remember is that yes, it can happen. Now, another thing is when you have accidental overlap of peaks, so one peak just accidentally has the same peak that another one has. Sometimes you can tease apart those peaks by changing the solvent. Okay, so the solvent that you record your spectrum in can have a big effect on the chemical shift. And big meaning, a tenth of a ppm, which is big, or maybe more. And so that's sometimes all you need to do. So you can sometimes tease the peaks apart just by doing the spectrum in a different solvent. There are 2 or 3 common solvents that you can pick. Please stop texting. Thank you. Okay, now determining the number of protons for an integral. I said that you get one of the kinds of information that you get from a spectrum is the relative numbers of protons that are stereochemically equivalent. So in that example that we just ran, this one, you would see a ratio of 3 to 1 to 1 to 1 to 3. Okay, so those would be the ratios of the stereochemically non-equivalent protons. And you wouldn't know if it's 3 to 1 to 1 to 1 to 3 or 6 to 2 to 2 to 2 and so on. You just get the ratio. Now the ratio, the way you see that ratio, a couple of ways. One way is you sometimes see a line integral. So in other words, you can program the machine to come along with, and it just kind of shows a line here, and then another line like that, and then the relative heights of those two horizontal lines represents the area under the peak, and then you measure the heights of those lines. The ratio is equal to the ratio of the areas. Or in some of the modern spectrometers, they just give you a little number under here. It gives you the same information, but the number you're looking at is the ratio of the areas under each peak. Okay, so in dimethoxymethane, the ratio is 1 to 3, but it's not 1 to 3, it's 2 to 6 actually, right? So now you need to be a little bit clever here. That if you measure the integral, you find that the numbers are, say, 1 to 3.03. They don't usually come out spot on the nose, right? Sometimes they're off by a little bit. Why is that? Well, because there's noise in the spectrum, and there are little sources of error and whatnot. So don't expect the integrals to come up exactly spot on, right? So you need to use a little bit of judgment here. And it becomes kind of tricky sometimes if it could go one way or it could go the other way. I mean, it's 3.03. None of us have any trouble saying, well, that's probably 3. But if it's 3.5, then, or 3.55, then we think, is that 4 or is it something else? And usually you can figure it out from other information. It's not that hard. Because why? Well, because the ratios of the protons have to come up with something real. In other words, if you have 3 carbon atoms and you run the ratios and it turns out you've got 20 protons, obviously that can't be, right? There's no way to attach 20 protons to 3 carbon atoms without doing real violence to the octet rule. And so you can usually figure this stuff out. So a few % error in the integral is nothing to worry about. It's normal. but just use judgment when you work up your data. So remember again that the integral doesn't give you absolute numbers, right? It gives you ratios. And so from the ratio, you have to use other information to get the absolute numbers. And now, for problem solving, one thing I left off here, and your book also doesn't mention, for the problems at the end of the chapter, you need to remember the little formula we talked about last time for units of unsaturation. Remember that formula? U equals 2C plus 2 plus whatever. Yeah, the first thing you need to do with those problems that give you an empirical formula, figure out units of unsaturation. And then from the spectroscopic data, you can usually tell, does it, especially if it gives you an IR, does it have a double bond or not? If it doesn't have a double bond, then it's got a ring, and so on. So that's usually where you start. Now, for the NMR part of the problem, start with the number of peaks. So you try to figure out, how many sets of peaks do we have? The number of the sets of peaks will give you the minimum number of stereochemically non-equivalent protons. Now, why do I say the minimum number? Well, because, as I said, you could have accidental overlaps. There could be more, right? So if you have 3 sets of peaks, then you can say, well, I have at least 3 sets of non-equivalent protons. There could be a 4th because, hey, one of those peaks might be overlapped with another one. So then from the integral, you determine the ratios of the protons. And then from the chemical shift, you determine what functional groups are likely to be present. Now, how do you use the chemical shift? Remember I sent out, or I posted on Lalima or whatever, that table of peaks. There's a good table in your book, too, and it looks like this. So if I look from 0 to about 10 or 11 ppm, I know that, say, benzene rings come in this region, vinyls here, aldehydes all the way alone by themselves out here, methyl groups are there, and so on and so forth. So I can use a table like this to figure out where to expect a methyl that's bonded to an oxygen or a CH2 bonded to an oxygen and so on. If you look at your solutions manual, they have a Curfy table too. And I'm not going to talk about that. You'll see that what that allows you to do is actually kind of nice. It's empirically derived. If I have a CH2, okay, CH2, and I have X and Y, then where X is whatever. It's either another carbon atom, an oxygen, a bromine, a vinyl group, whatever. I can look at the table, tell the table what X and Y is, and it'll make a prediction about where that methylene will come. And so that's actually quite useful to do. There are also NMR simulation programs that you can run on a PC that are actually pretty damn good. I mean, I'm surprised very often how well they reproduce, how well they predict a spectrum. So you can input a structure, draw a structure in, and say, okay, what's the predicted spectrum? We'll spit out a spectrum. And usually it's pretty close. The coupling is, and we'll talk about coupling in a minute, but even the peak positions are sometimes spot on. Okay, so as you're solving your problem, you need to write down all of the partial structures, okay? So if I know that it has an OH, just write an OH. If I know that it has a methyl, write a methyl. So at the end of this process, you're going to have all the little pieces, like a jigsaw puzzle. You'll have all the pieces, and now you just put them together in each way, in any way you can, all ways you can. Some ways are not going to make sense. I'm not going to square with the data. So some of the ways you assemble those pieces will make no sense at all. Discard. Once you think you have the right answer, be very careful. Then go back to the data and make sure that the data fit. It's very easy to fool yourself, okay? It's very easy to come up with an answer and say, oh yeah, this is it. Boy, on to the next one. And that's something you need to avoid. So you need to double check your answers and figure out, which answer satisfies all the evidence, not part of the evidence, all of it. Sometimes there'll be two structures that are very close, so this part is not always easy. Okay, now, the spectrum we talked about so far is dimethoxymethane. And as I indicated, and as you can see, that spectrum is pretty simple, right? I mean, there's not much there. It's got one line for the CH2s, for the CH2 protons, one line for the methyl, and it looks pretty simple. Now let's take a look at methyl bromide. Okay, so CH3, CH2Br, and these boxes here just are enlargements of these peaks. And so what do we see for that? Well, this looks a little different. It looks as if we have two packets of peaks. We have one packet that is shielded and one packet that is de-shielded. Okay, so just based on our discussion, and it gives it away here, but based on our discussion, the de-shielded peak is going to be which one? It's going to be the one that represents the CH2s that are bonded to the carbon bearing the bromine. Why? Well, because bromine is electronegative compared to carbon. What does that have to do with it? Well, here's what it has to do with it. The bromine is pulling electron density out of that carbon-bromine bond. Those electrons are not there to shield the CH2s, so the CH2 peak moves off to the left. That's why. The methyl, on the other hand, doesn't have that problem, and so it's more shielded, and the methyl comes right about where you expect the methyl group to come. So if you look at your table, and please don't memorize that table, you'll find that, yeah, this is in the right area for methyl. Okay, so far so good. Chemical shifts work. Integrals, well, I don't know if you can see this, there's a line here and there's a line there. The integral works out to 2 to 3, which is what it should. But what can we say about 4 peaks for this one and 3 peaks for that? Well, I'll make it simple. I'll give it away right now. So this is what's known as the n plus 1 rule, okay? N plus 1. What does that mean? Well, here's what it means. So n plus 1 rule. I'm going to draw methyl bromide. Again, I'm going to ask you some questions. Okay, so for this CH2, how many nearest neighbor protons do I have? Okay, 3. So this has 3 nearest neighbors. For the CH3, how many nearest neighbors do I have? 2 neighbors. Okay, so this is n. 3 plus 1 equals 4. 2 plus 1 equals 3. So the prediction is that this peak should actually be a quartet, and that this peak should be a triplet. Guess what? That's exactly what you see. There's a quartet, there's a triplet. Simple. Okay? So don't get fooled by the n plus 1 rule. It's that simple. So you look at how many nearest neighbors. It's 3. 3 plus 1 equals 4. Okay. So now, okay, so that's the n plus 1 rule, but it doesn't tell you where this comes from. So, but it does give you an idea of one piece of information that I mentioned, I guess, on Wednesday. And I said that the NMR spectrum is going to give you information on nearest neighbor protons, right? So here it is. That means that if I didn't know the structure and all I had was the spectrum, then I could look at this triplet and I could say, aha, that must mean that this CH3 has a CH2 next to it. Or I could look at this quartet and say, aha, that must have a methyl group next to it because 3 plus 1 equals 4. And so I can work backwards from the multiplicities of these peaks and figure out what I have. So here's another one. Okay, so this is dichloropropane. Now, the peaks here, the de-shielded ones, the ones that are downfield, are the ones that are next to the electron withdrawing chlorine. Chlorine is pulling electron density out of the bond. Those electrons are not available to shield these CH2s, so the CH2s here are de-shielded. The CH2 in the middle, on the other hand, doesn't have that problem, so it's shielded. Of course, you'll notice that it's now past 2 ppm, which means it's shielded, it's de-shielded relative to the methyl. If you look at your tables, you know that CH2s, and what I said in class, that it goes from CH3 to CH2 to CH in the spectrum. So CH3, CH2, CH. they get deshielded. So this is all, chemical shift is good. Now let's look at the multiplicity. But before we do that, let's make sure that this CH2 and that CH2 are stereochemically equivalent. Are they? Yeah, they are, right? Because if I take one CH2 and I color it, take the other CH2 and I color it, then those two are enantiomers. Are they enantiomers? No, they're identical molecules. And so those are chemical shift equivalent. So these two are chemical shift equivalent. This one is not. Okay, so this CH2 has how many nearest neighbors? Well, I have to count the 2 here and the 2 there, right? So 4. 4 plus 1 equals how much? 5. So if I count peaks here, I hope you can see, that's a quintet. And each one of these CH2s has how many nearest neighbors? Well, only 2, so each one of those is a triplet. And so if I had this spectrum, and if I knew just that this was a C3H6 chlorine 2 compound, be a snap to figure out just from the multiplicities and chemical shifts that, oh yes, it's 1,3-dichloropropane. Okay? So, now the N+1 rule, let's go over that again, right? And then let's figure out where it came from. So right now I know it's the N+1 rule because I said so. But actually that's not a good enough reason, so we're going to see why. Now first of all, you have to notice that there's no splitting between chemically equivalent protons, and we already said that. So the CH3 protons don't split each other, the CH2 protons don't split each other because why? Because those are stereochemically equivalent protons, therefore chemically equivalent, therefore chemical shift. That's why the CH3 protons don't split each other. That's why the CH2 protons don't split each other. It's also why these two don't split. These two show up as a singlet. Why? Because they are chemically equivalent. And so if they are stereochemically equivalent, they don't couple, they don't split. And so these two are singlet. Okay. Now that's one thing. Now the other thing that you need to notice is that the splitting is a short-range effect. And so most of the splitting is going to be of 2 types. Okay, these kinds of protons split each other. This is called geminal splitting, or coupling. Geminal because they're both on the same carbon, or they can be like this. And these will couple. This is known as vicinal coupling. So they're neighbors. So either they're on the same carbon or neighboring carbons. These are the kinds of coupling we're going to see. Now, if they're further away from that, so if I have C, like this, one here and one here. Okay, this is 1, 2, 3, 4 bond coupling, 4 bond. 4 bond coupling, usually we're not going to see. So 4 bond and 5 bond, you can occasionally see, but it's usually very weak. And so it's small, you don't usually see that. So it's going to be either 2 bond or 3 bond coupling that you see. 4 bond, 5 bond, usually not. Now, it changes a little bit if I have a pi bond here. If I have a pi bond there, then yes, I will see 4 bond coupling, and your book shows that. So, and that coupling can be substantial. Okay. But mostly it's going to be either vicinal or geminal coupling that we need to be concerned with. So protons like this normally don't split each other. Why? Well, because that's 4 bond coupling. And that's why we didn't see splitting here either, right? Because these were 4 bond. It would have to be 4 bond coupling. So remember, singlets and singlets, no coupling. Well, because they're too far away. Okay, now one thing that I didn't point out to you, but that I'm going to point out right now, that if you measure the distance between any 2 peaks in this triplet, any 2 neighboring peaks, obviously, or any 2 neighboring peaks in this quartet, you'll find that the spacing is identical. And in this case, it's 7.2 hertz. Okay, so that spacing between the two peaks of 7.2 hertz is known as the coupling constant. And that will allow you to tell if two peaks are coupled. Okay, because just imagine that we have a much more complicated spectrum. We've got triplet here, and quartet here, and quintet here, and something else. I want to know, well, okay, I see splitting all over the place, but which ones are coupled to each other? And the way you know is because the coupling constant, that splitting, is identical, only for peaks that are coupled. Now, it can be accidentally the same too, and that complicates things. But for simple things, it's a safe bet that if the spacing is the same, then they are coupled. Now, once again, if you're looking at a real NMR spectrum, the accuracy is, a tenth of a hertz you might get, but you might measure this and find that this is 7.25 and this is 7.19 or something. And so then you have to scratch your head and think, is that the same number or not? Because of noise. So you always have to use good judgment when you do this stuff. So in this case, in the case of ethyl bromide, the spacing between the peaks in the quartet and the spacing between the peaks in the triplet are identical at 7.2 hertz. We indicate the coupling constant of J. So coupling constant J means it's just the letter that we use to show coupling constant. So this is how you show the coupling constant. Now, coupled protons must have the same J value. I just said that. Now, when I say the same value, if you measure it on the spectrum, it's not exactly totally the same. Then you have a judgment to make. But if it's way off, then they're not coupled, and you know that. Now, the interesting thing is that the J value does not vary with operating frequency of the spectrometer. So the coupling constant, which by the way gives you an indication of the strength of the interaction, that strength of the interaction is something that nature gives you. And as it turns out, that whether you run the spectrum at 300 megahertz or 600, the J value is going to be the same. Not only will the chemical shift be the same, but the coupling constants will also be the same, but when measured in hertz. That's why we measure, you'll notice that we measure the coupling constants in hertz, not parts per minute. Okay, so if you measure the coupling constants in hertz, they're going to be the same in all spectrometers. Now, the other point that I didn't really make, that's time for me to make, take a look at this. These triplets are not, the peaks in the triplet are not all identical size. The peaks in the quartet are not all of identical size. And the peaks in the quintet are not all of identical size, but in all cases, what do you see? What's the first thing you notice? Look at this quintet, look at this triplet. Look at this quartet, look at this triplet. Something jumps off the page at you. What is it? Symmetrical. Yeah, you see symmetries, okay? So that, what I say about symmetry, I say whenever you see symmetry, it's important, right? So it's important here too. So here's why. Look, the relative intensities you can predict very nicely. And it's 1 to 2 to 1 for a triplet, 1 to 3 to 1 for a quartet, 1 to 4 to 6 to 4 to 1 for a quintet, and so on. And so the way you figure that out is as follows. You can do something called a Pascal triangle, which is kind of neat. Okay, so this is Pascal's triangle, and I've only gone down a few. If I go down here, 1, 4, 6, 4, 1. And you'll notice that this number is the sum of these two. This number is the sum of those two. This number is the sum of those two, and so on. So I can construct the Pascal triangle, and this will give me the relative peak intensities for quintet, quartet, triplet, and so on. So that's, if there are any math majors in here, you'll recognize that these are what? They are the coefficients of the binomial coefficients. And so if you don't like doing Pascal triangle, you can do it the other way. You just do it by figuring out the binomial coefficient here, where n is the number of nearest neighbors, and then you vary k from 0 to n. So n factorial over k factorial, n minus k factorial. So Pascal's triangle is on 13 too. In general, you don't need to do that because you know, what are you going to see? You're going to see triplets, quartets, doublets, triplets, quartets, quintets, occasionally a septet. Okay, but you know, it doesn't really go much beyond that. Why is that? Well, because think of it. How are you going to get 20 nearest neighbors without violating the octet rule? Yeah. Okay, so now you know. Okay, so where does this come from? Why? First of all, why are they split? And why the ratios of peaks? There's got to be a reason. So let's see if we can figure it out from what we've talked about. Okay, so let's take a look here. So you got a CH2, right? And you might have expected a single peak, because after all, we saw CH2 just a little while ago with dimethoxymethane that gave me a singlet. So, you know, it wouldn't be unreasonable to expect a singlet here, but it's not. And you'd expect a singlet, I suppose, to be right in the middle here. But what this is telling you is that these two protons, those two, which are represented by this peak, that they lead to a peak here, and one a little bit more shielded, and one a little bit more shielded, and one a little bit more shielded. And so what that tells you is that something weird is going on, because these two protons, they don't absorb at only one frequency. They absorb at 4 different frequencies, which means that they are experiencing not one magnetic field, but how many? 4. Because each one of these peaks corresponds to a different frequency, which means it corresponds to a different magnetic field. And so somehow, these CH2s are experiencing not one magnetic field, but 4 different ones. How did that happen? Well, actually, not that hard to see. Let's see if I can find the best picture here. That's worth 3. I think this is the best one. So let's take a look at, before we look at the quartet, let's look at the triplet. Triplet's a little easier, right? We have fewer. So I mean, same thing that I said for the quartet applies to the triplet too. Okay? So, so what we're going to look at is we're going to think about the applied field, okay? And the applied field is, cover this up, is in this direction. Okay, so I have applied field. Now, what I want to think about, and I'm thinking about the CH2s. Okay, so I'm going to look at the CH3 and I'm going to think about the CH2s. The CH2s for the methylene protons. So I'm looking at each one of these 2 protons. Okay, those protons have a spin, and that spin can be against the field, or it can be aligned with the field. So both against, both aligned. When I say both, I'm talking about 2 protons. So one of these little arrows is the spin of one of these CH2s, the other little arrow is the spin of the other CH2. So those can be either opposing the field, aligned with it. Or one can be opposed and one is aligned. But then it can also be aligned and opposed. So there are 2 ways to have one aligned and one opposed, right? It can be either the first one is aligned, the second one is opposed, or the first one is opposed and the other one is aligned. So I have 2 choices there. Now, the field that the CH3 experiences is a composite of the applied field plus this, or the applied field plus this, or the applied field plus that. And so you have 3 different fields that the protons in the methyl group experience, and that's why it's a triplet. Okay, and so the 2 that are opposed to the applied field are going to be, it should have been shown the other way around, are going to be shielding, and the other one's deshielding, and so on. And so the center of the triplet is where there's cancellation of the induced fields of the other protons. Now, put it the other way, if you look at the quartet, if you look at the CH2, then you have 3 spins or 3 fields for each of the methyls. And they can be either all opposed or all aligned, or 2 opposed and 1 aligned, or two aligned and 1 opposed. There's 3 ways to do that, 3 ways to do that, so 1 to 3 to 3 to 1. And so that's where this n+1 business comes from. It comes from the fact that the magnetic field that's experienced by any proton is some composite of applied field plus the induced fields, plus the sum of the induced fields by the neighboring protons. And so it doesn't, this effect doesn't go very far away. It's transmitted by bonding electrons. And so once you get more than 3 bonds away, you don't really see it, except under rare circumstances. So that's where it comes from. Kind of easy to see once you kind of visualize it that way. The other way to do it, your book I think shows it like so. This I think to me is less convincing. So you look at HA and HB. HA can be plus a spin and plus, or minus and minus, or plus, minus, minus, plus. But either way you look at it, it's 1 to 2 to 1 for the triplet. So a local magnetic field caused by the spin of the neighboring protons has an effect on the total magnetic field experienced by the observed proton. So this is just in words what I have written down, what I just said, that in one case the fields may be augmenting the applied field, or they can be subtracting from it, or one can be augmenting and one subtracting. And so the number of ways you can combine spins gives you the total number of ways, gives you the multiplicity of the peak. And that's why the binomial coefficients make physical sense. Now, this shows up. Yeah, it does show up actually. Let's take a look and see. No, it doesn't show up here. Now, there's a small, it's a small effect. We don't need to talk about that. It turns out there's a little preference, a small preference for plus 1/2 spin over minus 1/2. And because there's that preference for the plus 1/2 spins, it means that the relative intensities of those triplets, quartets, whatever, are not completely symmetrical, right? Turns out that there's a little bit of increase on one side over the other, and that comes from the small preference for the plus 1/2 spins. So this is pretty much spin-spin splitting in a simple case, but it gets more complicated. Now, one thing that the 6th edition has that the other edition does not is a discussion of Karplus curve. So I actually took a course from this guy when I was in graduate school. So the Karplus curve looks like this. It gives you the coupling constant in Hertz for vicinal coupling. Okay, so this is 3-bond coupling. And it turns out that the coupling constant varies according to the dihedral angle. Remember dihedral angles? We talked about Newton projections. Gee, I didn't tell you to forget about dihedral angles, right? So, okay, so the dihedral angle, in this case 60 degrees, in this case 180, is going to make a difference with respect to the coupling constant. So if you have dihedral angle of 180, or if they are eclipsed, then you have big coupling constant, 10 for eclipsed, about 12 for anti. If they're at 90 degrees, so in other words, if they're orthogonal, 0 coupling. And it's given by this cosine squared equation, where coupling constant is equal to a constant times cosine squared of the dihedral angle, and this constant varies whether you're on this side of the curve or that side of the curve. It turns out this is a very, very useful correlation, because you can actually tell a lot about chemical structure from the coupling constant, right? Because if the Karplus equation can be trusted, then that allows you to make a very nice prediction or a very nice interpretation of the conformation of your molecule, because you know the dihedral angles. If you have the 6th edition, take a look at that. I mean, you should know that the anti-conformer has the big coupling constant, and as you approach 90, that coupling constant gets smaller, smaller, smaller. And so we will pick up our discussion on Monday.